Okay, in these slides, we want to show how to get the potential difference between point A and point B using this integral that we talked about in the previous file. So how do we do that? Remember we said we need to create some path. We need to make a path. We need to choose any path we want. So we're going to choose this path. You go along the x-axis from A to this point at x equal to small d. And then you go from this point vertically upwards to point B. So we're going to choose this path for this particular problem. In the next problem, in the next file, we'll do a different path, and in the next file, we'll do an arbitrary path. So we'll choose different paths and see the result should be the same. Remember, the potential difference between 2 points has to always be the same numbered. So whichever path you choose, it should give the same answer. So let's see how to evaluate it on this path in a systematic way. So when you cut up your path into small elements of length dr, this is the first one, second one, third one, fourth one, fifth one. Of course, in reality, when you do the integration, that means you have to cut it up into an infinite number of parts. But of course, to illustrate the idea, I'm just cutting it up into 5 parts. And then we can then go from A to C, go from point A to point C. We can make this one part. And then we can go from C to B. You can always cut up an integration between A and B into 2 parts. Go from A to C, and then from C to B, because we're going on this particular path. And from A to C, it looks all motion on the x direction, so we can call that part number 1 of the path. And part number 2 of the path is when you go vertically upwards. So for part number 1, how can we characterize what's going on part number 1? If you go from this point to this point along all these points, the value of x changes, but the value of y stays the same. And the element of length dr, since it's on the x-axis, is just dx in the I direction, right? The element of length dr in this particular part is just dxi, and y is equal to 0. The y value of y at all these points is 0, and x goes between 0 and d. That's how to characterize what's happening on that part. So you substitute the electric field to be EI, so uniform electric field, EI, dotted into dr on this part is dxi. Now what's I hat dot I hat? 1. So you end up with E dx. And the electric field is uniform. So the electric field here and here and here, it's all the same value. So I can take the E out of the integration, and you're left with integration from 0 to d dx, which is just what? It's d minus 0, which is d. So the final result for the potential difference between point A and point B, it just turns out to be the electric field times the distance between A and C. Not the distance between A and B, the distance between A and C, because so this is what it turns out to be. And the next part, how do you characterize the next part? The next part will give you a 0. That's why I was saying that the answer is going to be already that part, because this part is going to be 0. Why is the integration from C to B going to be 0? Because if you look at what dr is going from here to here on this part, it's dy in the j direction. You're moving here in the j direction. But the electric field is in the I direction. And so dr is dy in the j direction. The x is the same value at all these points. And the y goes from 0 to small a. So if you plug in the electric field as EI and take the dot product with dyj, the dot product between I hat and j hat is 0. So you get 0. So actually this part doesn't contribute at all to the integration. So that's why only this part is the one that contributes to the integration. So the potential difference between A and B depends only on this distance between A and C. It doesn't depend on this part here at all. So this is the result. For the first part you get E times D, and for the second part you get 0. So the total just turns out to be E times D.